My name is Xinwei Gao. I'm talking about 3-5 optical quantum dots. To realize remote quantum communication, we need to consider qubit transmission with photons. First of all, it requires entanglement between local matter qubits and photon states. For this application, optically active quantum dots have advantages over other qubit systems. It has short optical recombination times, it allows fast spin control, and the wavelength of emitted photons can be transferred to fit for commercial optical fibers. A quantum dot is also used for fast spin control, but today I'll just focus on the correlation. I'll explain how the photon-electron entanglement is generated, controlled, and measured. I'll also point out a challenge I realized that has to do with coherence time. Finally, I will spare 2 pages for dot-to-dot entanglement with single photon interference technology. When we say 3-5 quantum dot, we refer to a kind of electron-hole system in semiconductors, such as indium arsenide or gallium arsenide. A quantum dot usually has 2 energy levels of interest. The ground level states are simply single electron spins. Above them are called trion states, both of which consist of 2 paired electrons and an unpaired heavy hole. The electron pair has total spin of 0. Therefore, a trion state is also a doublet state. In the presence of a magnetic field, let's say in z direction, the spin states will split onto different sublevels. Now, when a trion state transits to ground states, it simultaneously emits a photon. Here comes the point. The color and the polarization of the emitted photon is maximally entangled with electron spin state. The generation process is summarized like this. Assume there is a spin-up state. Under an effective Rabi rotation or a pi pulse, it flips to the spin-down. A pump laser with frequency omega will then excite the electron to the lowest trion state. Next, we can just stand aside and wait for spontaneous emission. Then we will get our entanglement. But that's not enough for quantum engineering. To utilize the entanglement, at least we still have to consider the initialization, observation, and coherent control. All the control signals are laser beams. They are generated in time order. Now let's begin with an entangled state psi. A long-lasting continuous wave excitation can read the spin-out and initialize the ground state as well. If psi collapses to spin-up state, then it will stay there as the pumping frequency is not enough to drive it anywhere else. If psi collapses to spin down state, then the CW field will pump it back to the trion state, then reproduce the entanglement. This process will produce extra photons in addition to the first spontaneous emission. Therefore, if any extra photons with whichever frequency are detected, then the spin down is read out. Otherwise, a spin up is read out. The transition cycle repeats until at one time the state collapses to spin up. The chance is 50-50, so if given enough time, it will always be initialized to spin up. After that, a pi pulse flips the spin up to spin down, followed by an excitation pulse that lifts the spin down to the trion state. Then the other spontaneous emission will occur, and then the period will go on. A spin control can be manipulated after the spontaneous emission and before the measurement. Specifically, a pi/2 rotation is used for entanglement demonstration. We will talk about it soon. You may have also noticed this 2.2 micrometer pulse. It lowers the photon energy to fit for optical fiber transmission. Here is an experimental setup that carries out the manipulation periods. Controlling pulses all go through the same optical channel before hitting the quantum dot. and the emitted photons are collected and measured by the left-hand devices. The emitted photons frequency is about 900 nanometer. The nonlinear optical device in this shadow area receives the photon and a 2.2 micrometer pulse. Then it gives out 1.55 micrometer light wave while conserving the polarization of input photons. By comparing the measurement results of the spins and photon polarizations, we see a strong correlation between photon states and electrons. However, the result here is not enough. We cannot tell if this psi is a pure state of entanglement or just a mix of two uncorrelated states. So the measurement has to be done in another basis. That's why we need this pi over 2 pulse. It rotates the electron state from the z-spin basis to x-spin basis. Correspondingly, the photon polarization is measured in rotated, circularly polarized basis as well. The correlation is also obvious. So at this point, the entanglement is successfully demonstrated. But the story is not end so happily. In comparison with the linear polarization basis, the correlation of the circular polarized basis is worse, and there is a reason. This is just my own opinion. Consider the time evolution of the entangled state right after it is generated. Let's forget about the global phase. If the photon is measured to be right-hand polarized, for example, then the spin state is approximately in this superposition. And the probability of getting spin x done is also dependent on time. And the worst case occurs when cosine is 0. In the above experiment, it didn't happen because the time t is short enough to keep the correlation. The oscillation frequency delta omega is the energy difference of two ground states. It depends on the strength of the magnetic field. In this paper, it is taken to be 17.6 GHz, so the period is about 50 picoseconds. But recall our target, which is to realize remote connection. If the photon propagates through a long distance, the time can be much larger than the oscillation period, and consequently the entangled information will get lost as the time becomes a random parameter. I think this is one of the problems to be solved if the photon-electron entanglement is applied for communication. So far we have talked about photon-electron spin entanglement of one single quantum dot. In fact, there is another way for three-level quantum dots to entangle with themselves. I call it dot-to-dot entanglement. It is based on the idea of single photon interference, proposed in 1999. Now suppose we have two separated quantum dots, dot A and dot B. We initialize both of them to the spin-up state. Then we give a short laser pulse. The pulse should be so short that at most only one dot is able to be excited to the trion state. After that, the compound state consists of three components. Then we put a detector somewhere between the two dots. Then when the detector receives a photon, it means one of the quantum dots must have been excited and have been experienced for spontaneous emission. So the lowest energy component is excluded upon this detection. The remaining state should be more or less entangled. The key point of this method is to blind the detector about which path the photon comes from. Because once this information is known, a detection has occurred and forced the overall system to collapse to one of the two uncorrelated states here. Using this single photon interference, together with the manipulation process we just talked about, a remote dot-to-dot entanglement can be achieved. And these are the references. That's all. Thanks for watching.